So the gas laws gave us this sort of toolbox which related pressure, volume, the amount, and the temperature of different gases, but it only did it two variables at a time. So it changed one and looked at the impacts of the other. And in each case, we sort of had this relationship between variables and this constant of proportionality, K. So what we can do mathematically now is just algebraically substitute all of these different, these three different gas laws, since they all have a common constant, and combine them into a single law, which is the ideal gas law. So let's do that. So I write up the proportionalities that we learned with the three different gas laws. So we know volume is directly proportional to temperature. We know that volume is directly proportional to the amount of a substance, and we know that volume is proportional to 1 over pressure, or in other words, is inversely proportional to pressure. So in each case, we have volume as the variable, and then its functional relationship to temperature, amount, and pressure. So we could also say then that volume is proportional. If we combine all three of these together to one term on the right side, we could say that it's proportional to, directly proportional to temperature, directly proportional to N, and inversely proportional to P. Right? This composite in green is really just a relationship of all of these three. It doesn't say that they're exactly equal, it just says they're proportional through some likely constant of proportionality. We could also rephrase this and multiply this both sides by P. That would give us PV is proportional to NT. So we're getting pretty close to something that might look familiar. This constant of proportionality then can be replaced and actually solved for, if we want to, for PV equals R NT, where the proportionality is set to an equal once we include this constant that takes care of our units, because we've got lots of different units here, and so the constant proportionality is dealing with that. This R here is the constant of proportionality, and we call this the gas constant. So let's think about what that gas constant is. So if we set this up and just solve, R equals PV over NT, then we can pop in the values for gas under standard state conditions. So we're talking about 1 atmosphere, and remember, for 1 mole of stuff, that equates to a volume of 22.4 liters, and 0 degrees is the standard state for a gas, which is 273.15. If we solve for this, what we end up with is a gas constant R equal to 0.082058, and that is in units of liter, atmosphere, mole, Kelvin, right? The atmosphere, liter, mole, Kelvin. So no mystery then where the gas constant comes from. It's literally just the constant of proportionality to make these numbers all equal each other under one condition. It doesn't matter what condition we use, they just all have to be reflected. So it's easy to just pick standard state here because we know what all of those should be under the standard state. There's multiple ways that you can express the ideal gas law. So I'm just showing you the different ways that you can express the gas constant here in a variety of different units, so don't be scared off. Probably the most common representation for this class is the one here. This is just a Wikipedia page here, the 0.082 in liter atmosphere per Kelvin mole. But notice there are lots of iterations here. Another one that's really common we'll use maybe a little bit in this class, but certainly when you get to Chem 108, is this 8.314. And notice the units are now in joule per Kelvin mole. And so there's ways to interconvert between units for various uses of the ideal gas law. I'll give you whatever units would be necessary and values of R that would be useful for whatever computation you'd use in this class, so you don't have to memorize anything. So as always, let's try to take this and apply it to a real example. So the question here is how many moles of methane are in a tank that has a volume of 100,000 liters at gas STP? And the second question is how many grams that would be. So let's write out what we know. So we know that we've got a tank and its volume is, I'm just going to write out 10 to the 5th liters, although just keep in mind that this has got, looks like 7 sig figs. Just shortening it up so I don't have to write that whole thing. Let's see, what else do we know? The temperature of this is going to be 0 degrees C, which if we're using a gas constant that's in Kelvin, we're going to want this to be in units Kelvin, so 273.15 Kelvin. We know that the gas constant here is 0.082058. That's liter atmosphere mole Kelvin. And we also know that the pressure is going to be 1 atm. So that's what we know. Pretty straightforward, plug and chug. So we can solve for N, which is the number of moles of this. So PV equals nRT. Solve for N. That's going to allow a rewrite to be PV equals RT equals N. Substitute these values. That gives us an expression like this. Let's go through and wipe out our units. So we've got our atmosphere, which goes from atmospheres in our gas constant, liters from the gas constant, Kelvin from the gas constant. That's going to leave us in units of 1 over moles, which is the same as moles, which is what we're looking for. So this value equates to roughly 4.461 times 10 to the 3rd moles of CH4. That looks pretty good to me. I think we've got 4 sig figs. We're limited by, depends. If you're given STP, you can assume that this 1 atmosphere has an infinite number of sig figs. Because it's STP, it's defined as 1.0000 infinite. So we won't constrain ourselves there. We'll constrain ourselves to, let's see, maybe 5 sig figs, which I don't know what this last digit is, but we could write this out with an extra sig fig to be consistent there. I don't have my calculator on me now, but that's what the value would be. If we want to compute this in grams, then we would use the molecular weight of CH4, and that would give us 7.157 times 10 to the 4th grams, which we could convert to kilograms if we wanted to. Either way, simple use of the. So a cool implication of the ideal gas law, there are many, but one that that I like to show in an in-class demo, which we won't see, but I'll give you a YouTube video of it, is what happens to the temperature of a system if the pressure goes up. So in other words, if you have this variable and you crank this up in the system, what's going to happen to this, assuming the amount of stuff stays the same, which it would. And so one way to model this would be to create a sort of plunger system where you have a gas chamber, and then inside that chamber you've got a plunger and a rod, essentially a piston, like what we've talked about before, where you can exert some force here over that area, or pressure. And so if you've got just normal atmospheric gas in here, so this can be done just in open air, so this is the atmospheric gas. What you can do is load the bottom of this chamber with a tiny piece of cotton. And the question is, can you get this thing hot enough just by using your hand to pressurize this, knowing that as the pressure gets cranked up, the temperature is linearly proportional? That's also going to get cranked up. Can you increase the pressure here high enough to actually get the temperature for combustion? Flash point of cotton is, I think, around 400 to 500 C. So quite hot, right, in an instantaneous way. So let me show you a video of that. All right, so in this demo, I've got a handful of these actually at CC. They look just like this. So in the bottom, this person's assembled this piston canister. In the bottom, there's a tiny little bit of cotton. So using just the force from his hand, let's see what he can do.
Press down quickly to increase the air pressure. The increased air pressure increases the temperature, making it